It's today. We're also thrilled to be joined by Sam's parents on Zoom. I wanted to acknowledge the importance of family support, and it's a tremendous journey to take the PhD. So we thank you for your support, and I know that Sam's really excited to celebrate with you soon. I'd also like to thank Sam's PhD lab mates, or as he calls it, the academic family. So we have Mitchell on Zoom, Zahapa and Erin here. And we're very grateful for the support of the dissertation committee. So on Zoom, we have Professor Christoph Kipp from Marquette University. And then we're joined by Stephen's colleagues here, Professor Damiano Zanotto, Professor Ravi Nataraj, and we're about to see Professor Yugan join us momentarily. So thank you for the continued support. Sam has carved his own research path into basketball, jumping and dunking, as well as spearheading our research in baseball biomechanics. And so his independent drive, coupled with his collaborative contributions, have helped us establish and lift the quality of our lab's research and culture. So amazing work. Sam has been recognized for his research in exciting ways. His first conference paper proceeding to an international conference led him to be selected as one of the very few finalists for a new investigator award for the International Society of Biomechanics in Sport, and later as a finalist for the World Athletics Best Paper Competition for the International Society of Biomechanics. At Stevens, he has been awarded the Competitive Excellence Fellowship, and I look forward to hearing about more recognitions to come. Sam has been incredibly productive. Each week during our meetings, he comes prepared with things he's learned conceptually, different things he's learned through exploring his data, as well as different updates for writing. And this has been consistent for nearly 5 years that you've been here. So it's amazing dedication and consistent contributions to your development that have brought you here. That discipline and drive and commitment to learning also has yielded many different papers. And we've had our share of paper journeys through the reviews, but Sam has 3 first author published papers, 3 first author papers in review, 1 co-author paper that's published and 1 co-author paper in review, as well as 3 conference papers and 10 conference abstracts, 6 of which he was the first author. So very productive. And Sam has also held 2 internships, one with the Major League Baseball Phillies and the other with Reboot Motion, both of which allowed him to study professional athletes, which is really exciting. Sam has also contributed meaningfully to the department and school through teaching service and student mentorship. As an educator, he's been teaching on weekends for the Art Harper Saturday program, which brings high school students to learn about the intersections between STEM and sport. And so he's been doing that for 4 years. He's also been a TA for senior design and a peer mentor for other PhD students. He's been a mentor in our lab for about 40 to 50 undergrad research projects and was recently recognized with the Undergrad Research Mentor Award at Stevens. So congratulations. I'm incredibly proud of Sam's accomplishments and his personal and academic development into an inspiring independent researcher. I look forward to celebrating the culmination of his dissertation. So without further delay, Sam, please present your dissertation.
All right, thank you, Professor, for the introduction. So I'll stand around here so I can gesture to the different content I'll show. So today, I want to describe how in my dissertation, I'm using analysis of impulse and momentum to understand sporting movements. Wake up, clicker. There you go. All right. So here's our outline for today. We're going to start with some general introduction of why we should care about sports-based research, and then that will end with each of my specific aims. Then I'll go on to talk about my 2 studies in the baseball pitching research branch, 3 studies in the basketball jumping research branch, and then finishing up with overall conclusion and significance. I'm happy to solve for any clarifying questions along the way, particularly when it comes to describing my results in greater detail. So when those slides come up, you're going to know it when you see it. And then please ask any clarifying questions. So why should we study sports? Sport participation is a double-edged sword for long-term health and well-being. On one side, it's good for our physical and mental health and allows us to connect with others. But on the other side, there's risk of injuries, burnout, and psychological distress. Therefore, sports warrant further research overall. Now, the two movements of interest in my dissertation are baseball and basketball, and they're also two of the most popular sports in North America. These sports involve complex, high-intensity, and repetitive movements, such as pitching a baseball and running and jumping with a basketball. And these warrant further analysis. So traditionally, the motivation behind sports science research focuses on either trying to enhance performance or to understand and mitigate injuries. In both baseball pitching and jumping, greater ball speed and jump height both correlate with greater levels of competition. Therefore, there are key indicators of performance in these sports. Additionally, injuries are also very common. So, for example, the upper limb injuries to the elbow and the shoulder in baseball pitching, and lower limb injuries to the ankle, hip, and knee in baseball and basketball jumping. And these form the standard sports science approach and motivations. But in the next slide, I want to introduce the central framework of analysis that I use in my dissertation to attack these research motivations and themes. So the central framework of analysis is the impulse-momentum relationship. This relationship describes how the external forces and moments applied onto our body change our body's linear and angular momentum. And it provides us a way to understand the fundamental movement control during sport-specific movements. Take an example of running, jump, and basketball. At the beginning of the jumping motion, the body has initial forward and downward momentum from the end of the running approach. And at the end of the movement at takeoff, the body has final upward center mass velocity that directly relate to jump height through projectile motion. In order to change the body's momentum from its initial state to its final state, each leg must generate ground action forces to overcome gravity and body weight. And they have to apply those forces over time. And that gives our measures of impulse. This is just a simplified example of motion in the vertical direction, but this also applies for angular movements, as you'll see later. The net linear impulse comprises of the ground action force impulse generated by each leg, minus the downward impulse due to gravity or due to body weight. And this is how we're able to get from the body's initial state of linear momentum to its final state and result in jump height. And this is all coming from Newton's second law. So why should we use the impulse momentum framework? What is it good for? Firstly, it provides insight into fundamental control of movement. And that is because successful execution of movements is predicated on and sometimes even defined by the momentum regulation of the task. For example, in a running jump, you can only successfully jump high and achieve jump height by redirecting the body's linear momentum from its initial state to its final state. And you can only do that by generating impulses against the ground. So once we understood the requirements of momentum regulation, then impulses provides us a strategy for how that coordination and task was being accomplished. In a different case, like baseball pitching, generating momentum or regulating momentum might not be an explicit requirement of the task, but it's a beneficial strategy. That's why all of the pitchers exhibit pretty consistent behaviors in terms of whole body momentum generation. Additionally, performance measures can also be measured by quantities of momentum. In the case of jump height, it's directly related to the center mass velocity at takeoff, and the velocity of the center of mass is simply the whole body linear momentum divided by the body's mass. So it's a mass normalized version of momentum. Similarly, fast ball velocity or ball speed in baseball pitching is represented by the momentum of the ball because the ball has a fixed mass. And by connecting momentum with performance, it allows us to understand how we get from the body's momentum to our ultimate performance measure. And lastly, because each task requires us to generate forces against our environment to regulate the body's momentum, those forces and the positions of the bodies that our body are in, as well as the joint loads, are all related Therefore, it provides further context in the positioning of the limbs, the joint loading of the limbs, and also context of injuries and the task demands. And there's one more unique context in baseball pitching and running jumps. So here's a visual I generated to represent momentum, or the amount and directions of momentum in baseball pitching. So I'll play through it and then explain what's happening. So here I'm representing momentum at the whole body level and for each body segment using different colored circles. Whole body angular momentum is represented by this black circle centered around the pelvis. So I want you to, actually I want to go backwards. So I want you to observe how at the beginning of the movement, you pretty much cannot see it. And then as the pitching movement evolves, the whole body angular momentum circle becomes larger and larger. It does go a little bit smaller, closer towards ball release, that I'll touch on a bit later. But the idea is that at the beginning of the movement, you have very small initial momentum for the whole body. And at the end of the movement, we have a lot more. And this indicated that the pitching movement has a requirement to generate momentum. In comparison, because the running jump movement is defined by the final two steps before takeoff, there is a presence of initial momentum of body. And therefore, instead of having to generate momentum from almost nothing, now there's a requirement to redirect the body's momentum. So this provides a nice contrast and comparison for how athletes leverage the laws of physics to accomplish tasks in slightly different contexts. So now we're moving on to our specific aims, sorry, which consists of more descriptive and hypothesis-driven components. First, we'll start with describing the roles of each leg in generating impulse in baseball pitching, and that will tell us how each leg was able to help us accomplish the task of generating whole body linear and angular momentum. Then we'll characterize whole body and segmental angular momentum during baseball pitching and investigate if they should relate to ball speed. So is more momentum giving you more ball speed? Then we're moving on to the basketball research questions with looking at the impulse generation basketball jumps and figuring out how each leg coordinates to generate upward and backward impulse to redirect the body's momentum. Then we want to leverage the impulse momentum relationship to answer the biomechanical, to answer questions comparing jumps without the ball and with the ball. And there's intuitive understanding that when we jump with the ball, we might jump lower, but we never know why. And the impulse momentum relationship allows us to explain why there might be a difference in performance by finding differences in either impulse or momentum. And lastly, we want to look at what things constitute as good jump technique or what biomechanical factors relate to jump height. And we're going to leverage some of the momentum and impulse measures, but also compare lower jumpers to higher jumpers and in jumps with and without the ball. So these are the 5 aims. Take a sip of water. You can digest. Okay, let's start with the first aim of the impulse analysis in baseball pitching. So here's a quick animation of the baseball pitch performed by a semi-professional player. The ground action forces of the back leg is indicated by the red arrows, and the ground action forces of the front leg is indicated by the blue arrows. Okay. Ball speed is an important factor for pitching success, and in order to generate ball speed, pitching was described to be initiated from the ground up through the interactions of each leg against the ground. Then momentum and energy are generated and transferred to the throwing arm until ball release. Therefore, the actions of each leg not only set up the pitching motion, but are also important parts of coaching emphasis. More importantly, coaching need to really respect the fundamental mechanics of pitching, particularly in how the roles of each leg are acting to redirect the body's momentum. You don't want to interfere with each leg's momentum generation by prescribing a specific cue. But the issue is the roles of each leg in momentum generation are either not known or not directly investigated in prior research. And this is when the impulse momentum relationship can be very helpful. because impulse summarizes each leg's contribution to the change in body's momentum. In terms of the roles of each leg in changing the body's linear momentum, it was pretty clear despite no prior investigation because previously the ground action forces were reported in literature. As found that the back leg generates a forward ground action force which propels your body forward, and the front leg generates a backward ground action force to break your body's forward momentum. So even though people haven't computed the impulse, we generally know what kind of impulse they will be generating. As for the angular side, it was way more descriptive and speculative. And it was said that the front leg serves as an anchor for transforming the vertical and forward momentum into rotational components. And that front leg play a role in creating rotational power. But how much of a role does it play, and does the back leg do anything? We don't really know. So it's more speculative and descriptive. Thus, the purpose of this study is to first quantify the roles of each leg in impulse generation during pitching, and then explore the mechanisms of angular impulse generation by each leg. And we actually looked at, in the full paper, we looked at both linear and angular impulse, but for the presentation today, we're going to focus on the angular impulse part because it's the major contribution. And also the linear results was pretty boring because this is exactly what we found. But in terms of the hypothesis, we have the front leg generating more given previous suggestions. So we have 4 male participants at the minor league level provide informed consent for this study. And they did self-selected warm-ups before a full body marker set with combinations of individual reflector markers and rigid body clusters with markers attached to it were attached to their body. And we need to have at least 3 markers per segment because that's what enables full tracking of the 3D translational and rotational movements for each body segment. They threw 6 to 11 fastballs amongst other pitch types in the lab, though we only analyzed fastballs in this study. They pitched on a standard-sized MLB practice mound that has force plate instrumented into it. And then the slope force plate was customized in its position such that it captures each participant's front leg contact despite their different stride lengths. And we record the 3D time synchronized motion capture and ground action force data in Motive software, and then exported it into MATLAB for processing. So here's what the ground action force time series looks like. We have the forces from the back leg in red, the front leg in blue, and the different marker types represent forces in different directions. This red asterisk here show that the back leg maintained contact with the mount, but unfortunately dragged off the force plate, therefore we cannot capture its full interactions with the ground. And our full paper will accounted for that to figure out how much of the force we're missing. The phase of interest is defined by the last dip, which is a bit harder to see at this time scale, the last dip of the vertical force, and then ends at ball release. And our reference system of interest, which defines the different directions for the variables, are defined by the objective of the pitch with horizontal forward going from mound towards the home plate or the target of the pitch, and the other axes defined accordingly. Our key variables of interest for each leg were the angular impulse that was generated by moment about body center mass and the body center mass positions. So here I want to introduce the concept of moment about body center mass. If we think back to our mechanics classes, we know that when we apply a force at an angle and a distance away from a pivot point, what does that create? That creates a moment and creates rotational movements. Now, similarly, when you apply a ground action force at a distance and an angle away from the body center of mass, which is a convenient pivot point, you also create what's called a moment about the body center of mass. And you can compute the moment about the body center of mass using a very similar equation to those using classical mechanics, by using the vector length from the center of mass to the center of pressure, which is the origin of the forces. And you do a cross product of that with the ground action force. And you can further decompose the cross product to reveal the angle theta between the two vectors, as well as the perpendicular distance for conceptual understanding. Then we can compute angular impulses as area under the graph for the moment about body center mass time series. And we do that separately for moments in different directions. So here's what the moment above body center mass in the area under the graph looks like for the back leg in red and the front leg in blue. And this is in the leftward direction, which is also the largest, and we'll talk more about that later. But that's how we are able to get our key variable of interest. All analysis statistically were performed in MATLAB. We did normality testing and then per t-test to compare impulses by each leg. So it's quite simple. So here I want to briefly describe the moment above body center of mass, particularly this leftward moment, because it's the largest for all of the participants and across all the directions. So here the moment actually starts out quite small as the forces were more directed closer towards the body center of mass and drives forward propulsion. Once the back leg force becomes a lot smaller and it's no longer directed forward, that's actually when moment begins to increase. And that resulted in the moment having its peak during the double support phase when it's actually directed backwards and the foot is dragging behind the body. Now for the front leg leftward moment, it starts out negative before being positive and then oscillating until bars. And we summarize these area under the graphs with these scatter plots, with the scatter plot of the angular impulse about the leftward axis, the back leg in red, front leg in blue, and that is the sum of the back leg and front leg in black. And we found that both legs back leg generated significantly more angular impulse about the leftward axis than the front leg, which means it contributes a lot more towards generating rotations, despite what was suggested previously. And thus, this contradicted our hypothesis of front leg doing. And we found these drastic differences from all four of our pictures. We also found different magnitudes of angular impulse in different directions. And directions are super duper important in biomechanics because it indicates very different things going. So the largest angular impulse that was generated was in this side view plane or in the leftward axis direction. And that is followed by angular impulse generated about the upward axis or in the vertical direction. Even though for a lot of the coaches, when they think about pitching, it's all about rotation generation this way. We're trying to twist the pelvis and then turn the torso. It's always the focus in this direction, even though the impulses generated here is much more, and sometimes it's twice as much. The smallest angular impulse generated directions were actually in this forward direction. And it's important to note because when you generate impulses or rotations in this direction, they are both responsible for forward acceleration of the pitching arm, which is the point of throwing. In the side view plane, this constitutes as a positive rotation. And the top view plane, this constitutes as a positive rotation. But for moments in this direction, it's really mainly for balance maintenance. So this is more the quote unquote the frontal plane, where it's maintaining balance from side to side, and it does not directly contribute to forward acceleration of the arm, which explains why it's a lot smaller. So now I want to talk about how we actually generate the moment on the leftward axis by breaking it down into each of the component variables. So here we have the moment about the leftward axis for all of the trials for participant 1 again. With A representing the time, and then here's the picture of what the body looks like during the time of peak back leg moment, and B being the time and the positions of the peak front leg moment. And that's across the trials. So we found that when comparing the ground action forces at the time of peak, the back leg has a much smaller force compared to the front leg, even though the moments generated are very similar, if not larger in the back leg. Additionally, the back leg also leveraged a longer distance vector R because the back foot is extended behind the body and the center mass is still translating forward closer towards the front foot. Therefore, the distance here is longer than the distance here. Oh, sorry, the distance here. Thirdly, if we look at the angle theta between the vector of the ground action force and this position vector, the angle for the back leg is a lot closer to 90 degrees, which is the optimal angle for generating moments, while the front leg has a small positive angle. So it's really a combination of a small force, long distance, larger angle. And when you apply a moment over a longer duration, That's what explained how the back leg was able to contribute a lot more towards whole body rotation generation compared to the front leg, even though front leg still did something. So this study had an obvious limitation of a small sample size, the pitches being thrown in the lab with no full pitching distance, and also no ball speed measurements. And we addressed all of these limitations with a published follow-up study that found pretty much the same findings, but in a group of high school pitchers. And some future work I'll touch on in the next section is when we look at how whole body angular momentum manifests in the momentum of each individual body segments. And if having more ball speed gives us greater performance. Having more momentum gives us more ball speed. So in conclusion, we found distinct roles of each leg in generating impulses to change the body's momentum. And the back leg was first responsible for propelling our body forward before creating rotation at the whole body level. The front leg was responsible for simultaneously decelerating the body and creating a little bit more rotation, though to a lesser extent compared to the back leg. And both legs leverage different mechanisms to accomplish the task of rotation generation. And this resulted in 2 publications that I was involved in. So what are the practical implications of these findings? During coaching, coaches often like to view the drag line that's created from the interaction of the back foot with the mound as a way to indicate how well pitchers use their legs during the pitch. And we provided a mechanical rationale because as the back foot is dragging on the mound, it's also a mechanism for creating a whole body rotation. Therefore, there's a reason that potentially maintaining contact with the mound for longer can be beneficial for the pitch, in addition to the benefits of having both feet on the ground, making you more stable. So we provided a rationale for reading the drag line, as was described in coaching. Another implication is in the discussion of stride types. Previously, coaches had described different stride types as, and even researchers have described it as either having a toe and fall method, where you remain a lot taller and having a longer, more extended back leg, compared to a dip and drive, where you lower more aggressively into the back leg and push yourself forward more. It's potentially likely that when we use a toe and fall method, by maintaining that distance, it can actually benefit the generation of moments. So these might represent different strategies to generate whole body momentum. So using the framework of analysis in this study, we can actually figure out if there are any benefits to the different stride types, and they are better for generating momentum in different pitchers. A shorter pitcher might have to use more of the dip and drive method because there's just less of a distance to begin with.
So can I just ask,
Yes.
are you saying that this could be a tool to sort of customize how one can improve their pitching?
It's first to quantify what's going on in their body during pitching, and to see does different movement strategies relate to different amount of momentum they were able to generate. And that is also assuming that maximizing momentum is a necessary thing. It's more so a helpful thing because there's a lot more going on in the throwing arm than just movements at the whole body level.
So presumably if you do this on at different levels of their, levels of their pitchings, do you see you can actually use as a tracking tool to how much you're improving from like the basic beginner versus intermediate to advanced professional levels?
It can go a lot further than that.
Yeah.
Because it really gives you a way to say, if I change my movements in this way, how does it affect the actual amount of acceleration and rotation I was able to generate? Should I experiment with different strategies and see what differences does that cause from a physics and mechanics perspective? Because right now, these are mainly examined through just looking at the videos or what's called position-based. But what really governs how we move through space is the interaction of forces and momentum. So it's applying fundamental physics and mechanics to analyze what's going on with these movements. So it goes a lot further than just tracking. It gives a lot more insight at a more fundamental level.
So it kind of gives a quantitative way to
Yes.
assess it.
All right, so now we talk about the other side of the impulse momentum relationship and look at angular momentum during baseball pitching. And by the way, that was my first study. So the other studies from there is getting a little more intense, just a fair warning. So it was previously described that whole body angular momentum was acquired from the ground somehow, and then transferred through the body segments. In my previous study, we reviewed finally the how of angular momentum was being acquired from the ground. It's through the generation of angular impulse. And that resulted in increases in whole body angular momentum. So natural follow-up question is, would having more whole body angular momentum result in more ball speed? Well, sadly, whole body angular momentum was not extensively investigated in prior literature because all of the previous research attempts had methodological limitations in how angular momentum was computed. So we were never able to gain a full grasp of what whole body angular momentum looks like without any obvious methodological issues. We can never see it clearly before. So another goal for my study was to characterize whole body angular momentum during baseball pitching and see what's going on. And I can briefly describe the methodological limitations a bit later. Whole body angular momentum also equals to the sum of each body's angular momentum, each body segment's angular momentum. And segmental angular momentum was believed to be a very important factor for quote-unquote pitching efficiency. But again, segmental angular momentum was never investigated deeply and thoroughly without any of the obvious methodological limitations, which is why another goal was to characterize what's going on at the segment level in terms of angular momentum. Another question is, will having more upper body segmental angular momentum result in more ball speed, given that it is described to be transferred from the lower body to the trunk into the arm? Oh, bless you. Previously, a lot of correlation analysis were done between angular velocity of different body segments and ball speed. It was found that maximum pelvis, trunk, and upper arm angular velocity correlated with ball speed. So we're wondering, will we see something similar when we use angular momentum? And is it potentially a more meaningful variable to track because it accounts for more things than just the rate of rotation? So I'll go into that in a bit more detail later. In terms of mechanics, ball speed should be closely related to the throwing up segment's momentum because we want to impart as much momentum onto the ball as possible at ball rates. So there's some backing from a just purely mechanical standpoint. Thus, the purpose of the second study was to characterize whole body and segmental angular momentum during baseball pitching, and investigate if there's any relationship between ball speed and maximum whole body and upper body segmental angular momentum. We hypothesized that ball speed would have significant positive associations with maximum whole body and each of the upper body segmental angular momentum about the leftward and upward axes. And as a reminder from the previous study, these two axes are more associated with the forward acceleration of the soaring arm. So we're mostly interested in momentum in these directions. So here in this study, we have 23 male high school pitchers with self-reported abilities to throw 75-mile-per-hour fastballs. Because some of them are under 18, they perform informed consent or assent, depending on their age. We have the exact same protocol with the same marker set being applied to their body. And these data were collected by our collaborators at Rush. So all of the baseball pitching data was collected by our collaborators. But this time, they pitched the full distance in an indoor practice facility, and ball speed was measured by radar gun. Yep, so I'll just skip on too quickly. We have the same protocol, we use the same mount, record the data in the same software, and then process it in MATLAB, all the same way. And our key variables of interest this time were the whole body and segmental angular momentum. And we also include the ball into the model of whole body angular momentum, even though it has a very tiny mass and a small radius. Our reference system of interest was defined exactly the same as before, but the phase of interest was defined differently, going from the max knee height of the front leg until ball release. And this was consistent within our cohort of pitchers and also with previous research. Shouldn't all come on at once. I apologize. So we can start from the top. So whole body angular momentum, as I explained before, is the sum of all of the body segments' angular momentum. And that's represented by this sum symbol here. And to find each body segment's angular momentum composes of a local term and a remote term. The local term is the product of the segment's moment of inertia I and its angular velocity. So that's the figure here. And this is usually what people are most familiar with a rigid body's angular momentum. But then there's also the remote term, and that is the cross product of this position vector R again, but from the center of mass to the segment center of mass. And the segment's linear momentum, that's why you see an M times a V, but then it's a linear momentum relative to the body's velocity. That's why you see the segment's linear velocity minus the body's center of mass linear velocity. And this describes the effect of the segment's translation or orbit around the body center of mass. And it's the combination of these two terms that describes fully how each body segment contributes to the whole body's angular momentum. To bring it back to the methodological limitations quickly, one previous study ignored this term completely. And they just thought, oh, it only includes the local term. And big difference. In order to fully compute angular momentum, we also used assumption of segment mass, intermass locations, and moments of inertia from previous biomechanical literature. So in terms of stats for this aim, we used linear mix models in R because they were able to handle repeated measures and the hierarchical structure of the data in consultation with the biostatistician at the lab. We used ball speed as the outcome variable, maximum angular momentum as the fixed effect, with the maximum being chosen from the larger of the positive and the negative peaks, and each participant as the random effect. And we also adjusted for multiple comparisons. Now for the results. Here I want to describe the profiles of whole body angular momentum about the left foot axis first. So if you remember from the previous study, the left foot axis is when things are the largest. Okay, so this is where we start. At the beginning of the phase of interest, whole body angular momentum was remarkably close to zero for everybody. And then it first goes into the negatives with the swing of the front leg. Then a bit later, it increases into the positives just before double support, which is the vertical gray line, until its peak during the middle of double support. As for angular momentum about the upward axis, also started off remarkably close to zero. And then it remained in the positives until its peak during double support. Thus, whole body angular momentum about the leftward and upward axes both reached their maximum during double support. And this was consistent for all participants. In terms of angular momentum about the forward axis, we noticed a lot more between participant differences. And the magnitude of angular momentum in that direction is also a lot smaller. So what we can say is at the beginning of the phase of interest, whole body angular momentum was very, very close to zero across the axes and for all of the participants. So our assessment of needing to generate momentum at the beginning of the pitch to result in much higher momentum at the end of the pitch was accurate. In terms of the size of maximum angular momentum across the axes, found that it's largest about the leftward, the smaller about the upward, and even smaller about the forward. So there's, yes.
Sorry, I'm a little confused about the direction of the upward axis momentum. Is that like rotating forward?
Yes.
Like,
yeah, I'll describe the different axes. So all of the axes are relative to the direction of the pitch. So if I'm throwing that way, that's where the ball is going. Then the leftward axis will be the side view. Okay. So to you, John, it will be this way, and any rotations in this direction, that will be captured by the leftward axis. The upward axis or the top view will be axis going straight to my body center of mass. We call it the transverse plane in biomechanics sometimes, but it captures rotation in this direction. And when we rotate our torso like this, it's captured by the upper axis. And lastly, about forward axis, it's like if I'm throwing that way still, if I'm going like this, that captures movement about the forward axis, or what's called the frontal plane in biomechanics. What's more annoying is that in pitching, you start facing side on, and then you rotate in multiple planes. So using the biomechanical standard definitions is less helpful. That's why we use the definitions based on the objective of the task. Does that help?
Yeah, so the reason that the upward axis momentum is always positive is that you start from the side.
And then you continue to rotate in the same direction around the body center of mass. So now we'll talk a bit more about the angular momentum of the different body segments. So the angular momentum of different segments are represented by the different line colors, and these are all mean and 1 standard deviation lines. And I'll highlight what to look at because it's quite a lot at once. So if your eyes follow these black boxes, initially we have negative head and trunk angular momentum for the upper body, and the front leg, foot, shank, and thigh segments for the lower body. And these occur at around similar times, but it indicated this forward swing of the front leg, as well as the backward bending of the head and trunk. As you see, we start off a little more upright and then it bends backward. Relative to the body center mass, that creates a negative rotation, a negative momentum. And this also explained why we saw the whole body angular momentum about leftward axis dipping into the negatives initially. Then those negative angular momentum decreased, and then the trunk and the head angular momentum continues to increase towards their maximum during the double support. And if you look at the trunk's angular momentum, it occurs at basically the same time point as whole body angular momentum. And that's because the trunk is the largest contributor to whole body angular momentum at the time of peak. And that was the case for a majority of the participants. And lastly, what's pretty cool is when you see the trunk angular momentum actually decreased from their maximum before we get to ball release, and that corresponded with an increase in the throwing arms segment's angular momentum. So what that tells us is that momentum is coming out of the trunk and into the throwing arm. In other words, it's a transfer of angular momentum out of the center of the body and contributing towards these being maximized and near ball release. So here, let's look at the results versus ball speed. So we did find whole body angular momentum has significant positive correlations with ball speed, only about the leftward axis. And that was the case for the whole body, the trunk, and the upper arm. Also, these are the linear mixed model results with the black line indicating the group level model. And each of the colors representing different participants, and each of the color lines representing each participant's trend lines. So it captures behavior at both the participant level and the group level to see overall, is it more beneficial or not? So even though we found significant positive associations, the effect sizes were all pretty small and the associations were quite weak. And we found no other hypothesized positive associations like with the forearm or the head. And there are some potential reasons for the lack of significant associations. So first was certainly our sample size, our choice of using the maximum magnitude, so that can be either positive or negative, though it's mostly positive. And lastly, the range of ball speed present in our population. So hypothetically, the statistical results might look a little better if we have someone that throws even slower and someone that throws faster towards the 100-mile-per-hour range, for example. Additionally, there can be participant differences in the distribution of momentum across different axes. And that's because we investigated momentum in different directions on their own. So some participants might have more angular momentum about the leftward axis that throws more like this over the top, where the others might throw more on the side. And as of right now, we haven't, frankly, we don't have enough people to really cluster them into subgroups based on their individual patterns. And lastly, if you remember from the crazy equation slide, angular momentum is computed relative to the body center mass velocity. But there can be participant differences in how different people use their body center mass. Some faster pitchers might have a very aggressive acceleration of the body center mass, and their angular momentum might actually be penalized because of it, whereas others might keep their center mass relatively still and just really throw their torso and arm forward. So these are all potential reasons for why we didn't find as strong a association as we've expected. All right, so in conclusion, in this study, we finally characterized whole body and segmental angular momentum fully. And we identified transfer of momentum from the front leg to the trunk, and then lastly, the throwing arm at ball release. maximum whole body angular momentum was largest about the leftward axis, followed by the upward and forward axis. And these were consistent with the objectives to generate rotations in these directions. Additionally, we found that ball speed has significant positive associations with maximum whole body, trunk, and pitching upper arm angular momentum, only about the leftward axis with small effects. And this has resulted in one paper in review where I also looked at the impact of prior methodological limitations. So what are the implications and future work for angular momentum? The first thing I want to say is that it's a very comprehensive and very complex variable. And in the context of pitching, it's still, we barely scratched the surface. So it's still very poorly understood. One future direction that I've tried to investigate is the alignment of angular momentum as a way to gauge at the efficiency of the pitch. So I have the similar video as before, but this only focuses when we have a significant amount of whole body angular momentum. And what I want you to focus on this time was not the biggest black circle in the middle, but really the circle for the throwing arm segments. That represents both the magnitude and the directions of the throwing arm segment angular momentum. And theoretically, if momentum is most efficiently transferred from one segment to the next, each subsequent segment should try to inherit momentum from the prior one, and they should be aligned in space. And when it is, these circles will be parallel with each other, and that's kind of what you're seeing between the forearm and the hand. These circles being more parallel to each other as the pitch develops. So let me play that. Play, thank you. Okay. So as the pitch develops, these circles becomes larger and larger, but also become more parallel with each other. And theoretically, this can be a way to look at pitching efficiency, but we're still trying to figure out a way to really quantify the alignedness or how well aligned the segments are in terms of momentum. Another implication is in using markerless motion tracking to understand pitching behavior with angular momentum. So right now, there's already technology that allows you to capture the movements of the body in games using what's called the Hawkeye data in this example. And it captures a very simple model of the body skeleton. So if you can look at this, it only has a single straight line through the center of the body segments. And this line of technology is called markerless motion capture. And for most of them, it only captures a simple model versus the full complete model we were able to build by attaching markers onto the body segments and measuring. This allows for capture of the segment's translation through space very well. But in terms of capturing the segment's rotations fully, particularly about the segment's long axis, is completely missing. In the full model, we can capture everything in terms of 3D rotation. But here, we can capture rotations in the other planes, but not about the long axis. So for things like this, the pronation of the wrist and the upper arm in this case, we don't know. We wouldn't be able to know how fast it rotates, even though in pitching, everybody talks about is how fast their segments rotates through space. So we did a quantification of how much momentum we're missing when we use this instead of this. And we found that if we want to use angular momentum, we're actually mostly fine. And that's because momentum was primarily, for example, momentum of the arms and the legs was primarily due to their translation through space, as opposed to rotation about their own center, about their own axis. So in that case, we're actually going to have very reasonable estimations of whole body and segmental angular momentum, even if we have a very simple model of the body. But still, the more important thing is in figuring out what we can do with this more fundamental, mechanically related variable before we want to implement it into a lot more complex models. All right, so that concludes the baseball part of our, yes. Do you have no question? All right, so that concludes the baseball part of my research. I am running out of water. That's fine, I got that one. So we'll first look at, now we're going to the 3 aims in my basketball jumping study. So we start with the impulse generation. And how jumps are being done. Then we'll compare jumps with and without the ball. And then lastly, look at what things can help us jump higher. So One thing I want to state immediately is that jumping is very relevant to sport, but also very complicated. It's an indicator of performance in all of these different sports. Here you see in basketball, in jumping, and in track and field. And repetitive jumping and landing were also associated with lower limb injuries. And from looking at the snapshots from these pictures from different sports, I hope you can see that jumping can occur in a variety of contexts. In the case of the top plot, you can jump, you have to jump during your offense and defense. You can jump for an object implement, such as a ball, basketball. And lastly, you can jump over an obstacle or a bar in high jump. Therefore, we should try to study jumping in as realistic context and as close to sport as possible. Now, stationary jumps are most common in sport in terms of the sheer numbers performed and also most heavily researched. But jumps from the running approach not only result in much greater jump height, but also but in exchange, places much greater demands on your lower limb joints. From an impulse momentum perspective, it requires you to redirect the body's momentum from its initial state to its final state. And typically, you can perform a running jump using one of these two movement strategies. The first one is called a 1-foot running jump, where you take off from one leg and go airborne. And there's a 2-foot running jump where you take off from a bilateral takeoff with both feet on the ground. And that's called 2-foot running jump. Compared to 1-foot running jumps, 2-foot running jumps have greater jump heights in a couple of studies, even though the studies were limited by the population they studied. It was in PE students, which is a classic in sports science research, and also one in volleyball players. But more importantly, 2 running jumps were found to have lower joint loading and also greater joint range of motion. Therefore, there are quite different strategies of movements. From an impulse momentum perspective, 1-foot running jumps require you to redirect the body's momentum exclusively with the leg in contact with the ground. But in 2-foot running jumps, there is an opportunity for concurrent coordination of each leg to redirect your body's momentum. Therefore, this opens up a room for multiple strategies to accomplish the task. And whenever we can see multiple ways to do the same thing, then we can compare them in terms of performance, in terms of strengths and weaknesses. So before my study, 2-foot running jumps in terms of impulse were only presented once in volleyball players. And it was found that the first leg in red, so it's the first leg to contact the ground, it generates a more upward impulse, and the second leg generates a more backward impulse. They thus play quite different roles to facilitate transfer of velocity, or what's really momentum redirection for going forward to upward. After my study was published, another paper on volleyball players revealed that the second leg actually generates a more backward and upward impulse, and then play a way more dominant role to redirect the body's momentum. So immediately we're seeing some diversity in what's possible. And what's important about figuring out why each leg generates how much impulse in which directions is because of its close ties towards jump technique and coaching, towards understanding joint demands, which helps us prepare the athletes, and understanding injuries and loads on different joints and different legs. So the purpose of this study was to quantify the roles of each leg in generating backward and upward impulse during 2-foot running jumps, applying a very fundamental mechanics approach to understanding how this task was done. These jumps were performed by basketball players for maximum jump height. And we hypothesized based on the study that was published before us that the first leg would generate more upward impulse, and the second leg would generate more backward impulse. We have 21 recreational to collegiate basketball players with 15 male and 6 females. They all provided informed consent with self-reported jump heights of at least 0.5 meter for male and 0.4 meters from females. And these were taken from previous studies on stationary jumps. And we expected higher jump heights when you run it with an approach. They performed self-selected warm-ups before a full body marker set was attached to the body with 3 markers per segment. But in this case, we prioritized attaching rigid clusters with markers attached to all their body segments and use the digitizing procedure to maximize the good data we have. To tell a funny story, since it's my defense, the first time I tried with individual markers on the first jump, 10 of them flew off. And I do not know which 10 they are. That's the most important thing. So 10 minutes after that, I was like, we need a different strategy to digitize the body. So adhesion in biomechanics is a very real problem. So I developed a real-time MATLAB digitizing code with the help of my lab mate, Mitchell, where we basically were able to take a precision manufactured probe and point it at each of the anatomic landmarks or the bony landmarks that define our skeleton. We go one at a time, allowing for direct contact with the bony landmark. And then we can digitize their position and post in MATLAB. That allows us to recreate the full scale, the full biomechanical model of the body with each of the skeleton endpoints. That's what allows us to compute all the biomechanical variables. The participants perform warm-up trials of jumps from a 15 feet of approach distance that is consistent with the NBA combined test distance. And then each of them has an adjustable hoop height within reach, such that it encourages them to jump as high as possible. They were free to select their approach direction and takeoff sequence. So in two-running jumps, you can either take off with the left, right, with the left foot being the first leg and the right leg being the second leg, or the right, left. And people do have different preferences. In both conditions, they were instructed to jump as high as they can. Though in jumps without the ball, they were asked to tap their limb on the hoop as high as they can. In a condition of jumping with the ball, they were asked to jump as high as they can while controlling the ball during the takeoff, and then dunk the ball into the hoop if they were able. They were instructed that we're mostly focused on the takeoff phase of the jump when you jump with the ball, as opposed to the actual finishing of the dunk. One reason is because it adds a lot more complexity to the research questions, but also they were jumping too high and the hoop was too high, such that it's outside of our capture volume. So we couldn't even see their hands when it's over the hoop.
So with the ball, are they dribbling?
So yeah, so they will be dribbling the ball during the running approach to avoid
And
a traveling. And then they were to control it. I do not specify how they were controlling it, even though people do argue in terms of coaching, different ways to control the ball and gather can have different implications for jump height. But since this is like the first one ever, just keeping it very simple. Just don't travel with the ball, don't have a violation in the sport of basketball before you go into a jump. So here's the phase of interest, where it's defined by the start of first leg ground contact, and it ends at takeoff. And we define the start and end events using vertical ground action force thresholds of 10 newtons. The reference system, once again, is defined relative to the objective of the task, in this case, the flight phase of the body. So the forward direction is defined by the center mass horizontal forward trajectory from the point of takeoff until you contact the hoop. And this allows us to directly relate the impulse we generate to how that manifests in the flight of our body center mass. And here's the ground action force time series for the back leg in red, front leg in blue, different markers representing forces in different directions. Our key variables of interest were the backward impulse generated by the first and the second leg as the area under the graph, and the upward impulse generated by each leg also as the area under the graph. And that's done throughout the phase of interest, or their ground contact really. We use linear mixed models again to compare the impulse between impulse generated by the first or the second leg, and each participant was the random effect. So here's the results of impulses in the backward direction for all of the participants. These scatter plots are the mean values of backward impulse generated by each leg in each trial. And if there is a red bracket, indicated that the first leg generated significantly more backward impulse than the second leg. And it's vice versa. If it's a blue bracket, and if it's no difference, then it's left blank. And we found at the group level statistics revealed that the first leg generated significantly more backward impulse, But when we look at the data from each individual participant, that was only demonstrated by 12 of the 21 participants, or over half, just over half. 5 participants had no difference in terms of statistics between backward impulses generated by each leg, and 4 had more generated by the second leg. And this contradicted our hypothesis because we hypothesized that the second leg would do a lot more, but we found that that was only the case for a small amount of people, and the others had a more even distribution or a shared role to decelerate the body's forward velocity. Now, in terms of the upward impulse generation, as you can see from all of the red brackets here, the first leg generated much more at the group level and for all the participants. So this supported our hypothesis. So one thing I wanted to highlight is the sheer diversity of impulse generation patterns that we can see in different kinds of interval running jumps. So this is what it looks like for all participants jumping. And the first leg, at the group level at least, was the predominant contributor to generate backward and upward impulse. In the middle row, which is done on volleyball players, it was found that the first leg was generating more upward impulse, and the second leg was generating more backward impulse. And for the study published after mine, it was found that the second leg, and that's the third row, they found that the second leg was the predominant contributor of impulse generation. So you can only imagine if at the whole leg level, these are how different the patterns of impulse generation are, what's going to happen at the joint level. It's going to be much, much different between the legs, between these studies and between the populations. So these differences can be due to something biomechanically, for example, the positioning of the limbs relative to the body center mass. I want you to draw attention to the positioning, particularly in this frame, of the back leg, the knees being much more bent like this, and the front leg positioning in front like this. It's looking nothing like the positionings of either of the volleyball or the basketball jumping studies. And that could explain how the furthest leg was not able to generate more impulses in this direction. It's too disadvantageous a position to be in to generate a lot of backward and upward impulses. Additionally, there can also be differences in each group of participants' training history and how they learn to jump, also any potential injury histories. And lastly, there can also be task differences that augment how impulses are generated. For example, in the middle study, they were asked to jump as high as they can and spike a suspended volleyball as hard as they can. That might impose an additional need to impose horizontal momentum onto the ball. And that could augment how they were interacting with the ground as they were in contact with it. So these are all the potential reasons why we can see very different patterns of impulse generation. So in conclusion, we found that the first leg was responsible for generating more upward and backward impulse. Though in terms of backward impulse, we found participant differences. Some future research directions that I will talk about today are differences in impulse generation between jumps with and without a ball, and impulse versus jump height in jumps with and without a ball. So how are things different when we jump with a ball at an additional constraint, and how does it relate to performance? And this has resulted in one paper in the Journal of Biomechanics after much struggle. Okay, so what are the practical implications of this research? Well, when people are learning to jump higher, including me, we're almost always focusing on an optimal technique. What's the technique for jumping as high as we can? And we always think about technique as a set of positions that our body needs to be in. But what really matters for jump performance is how much impulse we can generate against the ground to redirect our body's momentum. Therefore, the movements the athlete chooses arises from the interaction between the requirements of the impulse generation of the task, what movement library or what movement options is available to the athletes in terms of their strength, coordination, and their structure, and also how much they've practiced a specific task. Therefore, by looking at impulse generation and using that as a framework, it provides a fundamental perspective to view technique, where it shouldn't really be about whether our legs is in a specific position, but how well we're able to redirect our body's momentum by generating forces against the ground. So it's a different way of thinking technique when we are training to jump higher. Additionally, the impulse generation requirements of the task also have direct implication of the loading of the joints because it enforces different ways that our body interacts with the ground. So I did some preliminary investigations of joint kinetics or the loading onto each joint during tuber running jumps with each leg. And we found very, very different profiles of not only the different contributions of the joints, but also which joints are going through how much moments, how much force at which time. And that's because the impulse generation was very different compared to prior studies. So if that's very different at the whole body level, it's really no surprise that at the joint level, things are even more different. So by taking this framework, we're able to account for why, or like what kind of impulse the task requires to generate to contextualize technique and joint loading. So now I want to talk about what's different between jumps with and without a ball. And a little bit later today, I'll be doing both of these. So I'm looking forward to that as well. So in jumping in basketball, it can be performed without a ball, which is similar to a baseline task where you can have a free use of an arm swing to go up into the air. But when you jump with a ball, particularly when there's a need to control it, you have restricted arm swing and the attentional demands to hold on to the ball, not to mention other things that will happen in the game. Might also be other biomechanical changes that's a knock-on effect as a result of holding it. So because of that, there's always an intuitive understanding that when we jump with the ball, we should jump lower. But then the question is, why is that the case? And is there anything we can do about it to make sure we don't jump lower as much as we do? So the closest comparison we have to jumping with and without a ball with restricted arm swing is a comparison of counter movement jumps with and without the arm swing. And it's like a crowd favorite comparison in the literature. They love to do these studies. And all of the research consistently show that when you jump with an arm swing, which is what it looks like on the top row, you have greater jump heights, which is not too surprising. And it was due to two mechanisms at the whole body level from biomechanics perspective. It was due to higher center mass height at takeoff and higher center mass upward velocity at takeoff. The higher center mass height at takeoff is sensible, because if we look at the posture or the configuration of the body segments, when your arms are going to be overhead, it brings your center mass higher compared to when your arms are by your side. So that explains the first point of why the center mass height is higher. Now, secondly, the center mass upward velocity, that is modulated by the impulses we generate because of the impulse momentum relationship. So it's found that the higher center mass upward velocity was due to a higher net upward impulse. And that was actually due to a longer duration of ground contact as the participants maintained similar average upward ground forces. So if you remember the equation for impulse, it's the area under the graph for forces, but it's also the product of ground contact duration and average force. So average force was maintained, but the duration component was modulated between these two different tasks. All right, so the purpose of this study is to examine the whole body biomechanical differences between jumps with and without a ball at both the whole body and at both the group level and the participant level. We made sure to look at the participant level because of the previous differences in participants that we found in our previous study. And we hypothesized that when we jump with the ball, we have a lower jump height, and that can be explained by a lower net upward impulse. So we used the same data set as before with the same data collection protocols. And the only difference between this and the prior one was that we analyzed both jumps with and without a ball, as that was our comparison of interest. We used the same reference system and definitions of the phase of interest. And our key variable here are the net upward impulse through the total ground contact phase. And that is the sum of the upward impulses generated by the first and the second leg and the negative body weight impulse due to gravity. And as an aside, this downward impulse due to body weight was proportional to ground contact duration because of our body's fixed mass. And it's a way to account for the effect of gravity on our body's movements. Additionally, we're also interested in the context of the initial momentum condition through initial downward center mass velocity, and the final momentum condition through the final upward center mass velocity, which also is our measure of jump height through projectile motion. And because of the impulse momentum relationship, final upward center mass velocity is directly equal to the sum of initial downward center mass velocity plus the net upward impulse divided by mass. So it all fits into one equation. Any changes in these two variables can explain changes in this higher level variable. Again, we used the linear mix model, and then we compared each impulse momentum variable with the condition as the fixed effect and the participants as the random effect. So here's our group level findings of jump height and final upper center mass velocity. And as a reminder, they are pretty much the same thing because of the direct equation you use to compute. So we found that when they jump with the ball, which is indicated by the orange, because the orange color of the ball, they were jumping significantly lower at the group level with significantly lower final upward center mass velocity. And it's quite a lot lower. And when we track to understand why they were jumping lower through the component variables, it was due to significantly lower net upper impulse, not significant differences in initial downward center mass velocity. And this was consistent with our hypothesis. All right. Now here's the juicer. So this is the participant level data, and I'll explain how this plot is arranged. So we have the table at the top that summarizes the comparisons for each variable between jumps with the ball and without the ball. If there are no significant difference between the conditions, it's left blank. If there are significant differences that explain the why we're jumping lower with the ball, it has a thick black arrow. If there is significant difference in the other direction, it will be marked as a gray arrow later on. Okay, you don't see it yet because this is only one person's data. Now for the scatter plots, we have the net upper velocity in this purple color in star. And then we have the final upper center mass velocity in the upper triangle just below. And the initial downward center mass velocity as a downward triangle. Because they were all part of the impulse momentum relationship, they can all be visualized on the same plot. And they were aligned, they were arranged in such a way that the vertical order is consistent between the table and the scatter plots. If they were from jumps without a ball, they were left blank. If they were from jumps with a ball, they were filled in orange. So basically, we wanted to see how can we explain a dip in the final upper center mass velocity scatter plots, this triangle. How can we explain it? Is it because of more of this or less of this and less of that? That's how we were using these figures. For participant 1, we already found no significant difference in their net upper impulse. And the reason they were jumping lower was because they modified their initial condition. They have more initial downward center mass velocity that explain their lower jump heights. Now here's the data for all the participants. I just want to quickly highlight, these are the gray arrows with significant differences in the opposite direction, where it does not help explain why we're jumping lower. So I'll draw your attention to the black rectangles. For the significant group level results of people jumping lower, that was exhibited by 18 participants. And 3 actually managed to maintain their task performance across the tasks. Of the significant level group results of lower net upper impulse, it was shown by 15 participants, that's marked by this rectangle. 6 participants had no difference in how much impulse they generated. And lastly, it was not captured by the group level statistics, but 6 participants had higher initial downward center mass velocity, indicated by here, with 3 participants having the changes in initial downward center mass velocity being the explanation behind why they were jumping lower. So if we had only used group level statistical measures, we'd never be able to figure out why these 3 people were jumping lower. We just wouldn't know. Additionally, as a final thing, Mechanically relevant differences might not be shown statistically. So let's look at participant 18 here. This participant jumped significantly lower, but it was neither explained statistically by differences in either net upper impulse or initial downward center mass velocity. And that's because as the participants perform the task, there can be trial to trial variations that's inconsistent in any of the two variables. So in that case, some of the trials might have had less net upper impulse, and some of the trials might have had more initial downward center mass velocity. But that's why you can have mechanically relevant differences that resulted in lower jump heights, but we cannot capture them fully with statistics. So now let's look at why they were generating less net upper impulse. And by looking at the group level data, we found that the lower net upper impulse was due to lower second leg upper impulse only. And what's happening at the participant level? So let's take another look. Once again, we have the tables summarizing each comparison between jumps with and without the ball. First legs are represented by the red, second leg in blue, the black blood void downward impulse represented by black. And we saw that for the first participants, there were no differences in any of the three impulse variables statistically. Now for all of the participants' data, I want to draw your attention to the group level significant results, where we found that 7 participants, only 7, had lower second leg upper impulse in jumps with the ball, with 13 participants having no difference, and 1 having difference in the opposite direction. But they actually somehow managed to generate more impulse during this task. 3 participants had significantly lower first leg upper impulse when they jumped with the ball. Interestingly, 4 participants had higher downward impulse due to body weight. And if you remember from before, this term was computed as the product of the body's mass and duration of ground contact. So what this tells us, particularly for participants 13 through 15, they were generating similar amount of impulses by each leg, but it took them longer to do it. What that means is that they have a lower average force. The average force for them during the ground contact was lower, and that actually resulted in lower net upper impulse and therefore lower jump height. So it's not really about staying on the ground as long as possible. You're trying to defeat gravity. So what you want is generate as much force over the downward acceleration due to gravity that you can. Now, interestingly, for participant 12, she was the only person that was able to generate more impulse with the first leg with a longer ground contact duration. But because she also had less second leg upper impulse, overall, the net upper impulse was lower. That explains why she jumped lower. So to quickly summarize, lower net upper impulse were primarily due to lower average upward ground action forces. And that's detrimental to jump height. So what about the 3 participants that somehow managed to mitigate any differences in jump performance? I found that as participant 19, which is the one marked by the black triangle, this participant modified their initial conditions in a beneficial manner to offset the lower net upper impulse. So they were able to change both of the variables in opposite directions to maintain performance of jump height across the tasks. As for participant 20 and 21, they maintained similar generation of net upper impulse by maintaining similar average ground action forces. So it is possible to do it. And lastly, participant 20 also maintained similar initial conditions by maintaining similar running approach characteristics. So in conclusion, we found that group level results, if we only use group level results, we found that when people jump with the ball, they were jumping lower, but it was mainly due to lower net upper impulse from the second leg's upper impulse. That's if we only use the group level statistical results. But what the participant level result reveals is that pretty much any variable that can be different was different for all of these 21 people. Final upper center mass velocity were not always lower, but when it is lower, it could be due to more changes in initial conditions or differences in their upper impulse generated. And that's indicated by all of these P, representing participant level results. So what are the implications of these kind of work? Well, when we're studying more sport-specific movements, such as a running jump with a ball, compared to a more traditional and standardized movement, such as a stationary counter movement jump, we should not only expect, but embrace participant differences in how they're going to be moving. The closer we get to sport-specific movements, the more their training history matter, how they were learning to jump matter, and the amount of specific practice matter, right? And speaking of specific practice, pretty much all of the dunkers that were training to jump and dunk, all the basketball players, they always fall for this mistake. So when they were initially trying to dunk, they would just go and touch the rim. And they'll go until their wrist is just above the rim. They're like, oh yeah, surely I can dunk now, right? And then the moment they have a ball in their hand, they jump drastically lower and it's not even close. So this study, I hope I've demonstrated a wide array of different biomechanical differences between the tasks that's exhibited by a group of skilled basketball players. Because there are so many biomechanical differences between the tasks, specific practice is even more important. If you want to be able to jump higher with the ball to dunk, you need to practice that specific task. And that's the only thing that can help you bridge the gap in performance between when you jump with the ball, without the ball, and with the ball. So now we are going to our final A, looking at biomechanical variables such as jump height. So starting with the impulse again, it was only presented once against jump height in prior research. And we've only found that the second leg generated more impulses, which is what we found here, and correlated with jump height, in addition to the total vertical impulse generated by both legs. And this made sense because in that study, the second leg generated a lot more. If you remember, in my study, the first leg generated a lot more, particularly backward and upward impulses. So we should expect different relationships between impulses and jump height in our group of participants. Now, people like to focus on the kinematic variables relating to the initial condition because it might be more modifiable. So one of the crowd favorite variable is the initial force and the mass velocity. And jump height correlated with initial force and the mass velocity from the end of the running approach in jumps and volleyball, high jump, and the long jump. So that's a variety of jumps in different sports using both legs and one leg. And this was because that the running approach speed allows the athlete to better leverage the lower limb stretch running cycles, which ultimately enhance core action force and impulse generation that determines jump height. Though it is worth noting that this velocity is going up to the maximum controllable velocity by the participants. So it's not just about running as fast as you can, we're really using as much as you can. Another variable that's related to that is the foot's anterior positioning relative to the body center mass. And we call that the plant angle. And it's an angle measured by how much in front of the body the foot goes at the time of first leg ground contact. And it was found to correlate with jump height, when once again, jumps in volleyball, and also the long jump and the high jump. And this is because it positions the leg to prepare it to generate upward and backward impulses, even as the center mass continues to move forward. If you have a contact of the foot closer to under the center mass, then you have pretty much no time until your leg is behind you, and it becomes really, really hard to generate meaningful backward and upward impulses. It's particularly backward. However, to have a more shallow, a smaller plant angle, or more anterior foot, it requires more control and strength at that more extreme limb configuration. The last variable that people have looked at a lot in terms of kinematics was the center mass ascent distance, which is measured by the distance traveled from the lowest point of the center mass during ground contact to the center mass position, center mass height at takeoff. And it was found to correlate with jump height in jumps in volleyball and stationary counter movement jumps and the high jump. And there's a very fundamental reason for this, because when you have a longer center mass ascent distance, there's a longer duration for you to generate impulse while the center mass is already traveling upward. Thus, all of the impulse you generate directly contribute to increasing your body's final upward center mass velocity. And that would directly increase your jump height. Yes.
How important to the center of mass ascent distance is the raising the arms above the head? And does that need to be like controlled in any way? Or is it just something that you just take into account?
Yes. It helps a lot. And we don't even need biomechanics to do it, because sometimes when you observe a behavior that's so universal, whenever people are trying to jump as high as they can, this is something they maximize instinctually, naturally. And the biomechanical explanation is yes, the more outstretched your whole body is, the higher your center mass height can be. And that directly benefits center mass ascent distance, which indirectly benefits impulse generation and jump height.
I mean, like differences in between people, like does it matter whether they're fully outstretched or if it's like kind of bent at
So
the elbows? Or
it matters in terms of when you compare biomechanically the differences between them. But within an individual, they can just have really tight lats and shoulders, right? So even though they're trying their best to raise as high as they can, but they can only access so far. So if we're looking at purely from a biomechanical perspective, it can be beneficial, but the difference in terms of your center mass height from here to here probably isn't as big a difference to, it's probably not too meaningful. It might be like 1 centimeter, but 1 centimeter in terms of like your jump height is not that much of a difference, right? So that's another consideration. So the purpose of this study was to examine the correlation between jump height and the kinematic and kinetic variables of interest that we just talked about. And we also like to explore the correlations in both jumps with and without a ball. We hypothesized that jump height will have significant correlations with initial force, center mass velocity, plant angle, center mass ascent distance, and the different impulse, backward and upward impulse variables that we compute. The last time we had the same participant in the protocol, where we also analyzed both jumps from without a ball, and then we have the same definitions of phase of interest, the reference systems. And for our key variables of our interest, it was largely similar to what we had before. And the additions are the kinematic variables, where the plant angle is defined by the angle between a vector from center mass height to the heel marker, and then the backward horizontal marker. That gives our angle theta for the plant angle. And center mass ascent distance is computed as the difference in center mass vertical position between the lowest point and the highest point at takeoff. And it's like this is during the ground contact. So we don't consider the highest point as the phi phase. This time we use MATLAB for a more simple statistical measure, where we did normality testing, and if the data were normally distributed, we use Pearson's correlation. If not, we use Spearman's rank correlation. And we compared the correlation between jump height and each variable of interest. So here we have the results for jump height on the y-axis. And we actually notice that we have a much larger range of jump heights compared to what we have access to previously in baseball. And then we have the initial force and the mass velocity along the x-axis. The data from jumps without a ball is in black, one jumps with a ball is in orange. And we found very strong positive correlations between initial force and the mass velocity and jump height in both conditions. And these were consistent with prior research. Additionally, we also found significant negative correlations between plant angle and jump height. And it's negative because a more anterior positioning of the leg will result in a smaller angle. So what this tells us is that higher jumping athletes, they were able to use more initial force and mass velocity and a shallower plant angle. And that the athletes leverage similar mechanisms at the whole body level to generate jump height in both conditions. The practical implication for this is that we should eventually learn to use more initial force and mass velocity and shallower plant angles over time, as that's what it seems like with better jumping athletes. And we can do that by first experimenting with a range of different initial force and mass velocities and plant angles for the benefits of differential learning, which helps skill enhancements. And also another thing is to develop the strength and mobility that can eventually allow us and support us in the use of more initial force and mass velocity and more extreme plant angles. We also found significant positive correlations between the center mass ascent distance and jump height in both conditions. That was consistent with a lot of prior research. And the practical implication is that we could try to increase center mass ascent distance by manipulating our center mass height and initial contact, as well as modifying our running approach and initial conditions to try to experiment with this variable. In terms of correlations between net upper impulse and jump height, for net upper impulse, it's most mechanically related to jump height, so it's very strong positive correlations were not surprising. But what's more interesting is when we look at the correlation between impulses generated by each leg and jump height. And we only found significant correlations in jumps without the ball for both legs. So if you remember, I want to touch on this quickly first. So finding a first leg upper impulse that was significantly correlated with jump height went against the one prior study. And that's because we generated a lot more upper impulse with the first leg compared to the second leg. And that's what you can see on the scatter plots here as well. And this tells us how the contributions of each leg towards jump height was certainly influenced by its impulse generation patterns that you have. So because our impulse generation patterns were different, we captured a different relationship statistically. Now, if you remember all of the participant differences in upper impulse generation in jumps without the ball, with and without the ball in the previous study, that should help explain a little bit more why we didn't find any significant correlations when looking at impulses generated by each leg versus jump height. So the practical implication for this is that we should just try to maximize the net upper impulse as a whole, rather than worrying about the specific impulse patterns that you may have by each leg. And net upper impulse can be increased by doing strength training in conjunction with doing specific practice of these tasks. In terms of jump height versus backward impulse, we found that for the net backward impulse for both tasks also has significant positive correlations with jump height. And this is mainly because higher jumping athletes were simply able to generate more impulses against the ground. And this also indicates that they have a better control of the initial force and the mass velocity because of what we found in the relationship between this variable and jump height. When looking at the impulses generated by each leg, we still found significant positive correlations, but also in this case, for the second leg backward impulse jumps without the ball. But mainly it's to highlight that there are multiple valid strategies to generate backward impulse, and focusing on these is really less important in practice compared to generating overall net backward impulse to control the body's velocity. Therefore, we should try to improve overall impulse generating capabilities and realize that backward impulse generation is really playing just a supportive role towards jump height, and that we should try to control initial force and mass velocity as it's only useful as they can be controlled. A lot of times, if athletes are struggling to control their initial force and mass velocity because they have a limited braking ability or limited ability to generate backward impulse, the simplest suggestion would be to slow down. And that because slowing down reduces the demand of backward impulse generation, which a lot of times actually helps with jump height. And in teaching my professor and my lab mates how to jump during the lab meetings on Fridays, the first suggestion is always to have a shorter running approach and lower speed, aka slowing down. And they were actually able to jump higher, even though you're no longer running as far to prepare for the takeoff. So in conclusion, we found that in both jumps with and without the ball, jump height has significant positive correlations with the initial force and mass velocity, plant angle, center mass ascent distance, and the net impulses. In terms of kinematics versus jump height, it was consistent with both jumps and volleyball and the other one for running jumps. And it highlighted how similar biomechanical factors are leveraged in running jumps in general. In terms of impulses versus jump height, our findings of impulse versus jump height for each leg were more specific to the patterns of impulse generation that we found in our studies. And that we should prioritize generating more overall impulse over focusing on any specific impulse generation patterns or trying to correct it. And this paper has resulted in a one-paper review with the frontiers of sports and active living. Now, for future work, I only briefly examined the whole body biomechanical variables that were most commonly investigated in prior research. But because it's a running jump, other characteristics of the running approach could also change running performance. But because we were limited by the space in the lab, we can only investigate this task in a shorter running approach. Additionally, there's also questions of the timing, rhythm, and coordination of this task, as the post data collection interviews with different participants always reveal that they say the timing, the feeling, and the rhythm of jumping is one of the most important factors in terms of their jump performance, but it's actually really difficult to quantify. So that's something future research should also tackle. And lastly, here's actually the video of the highest dunk with the ball this season in basketball. And it was actually captured using markerless motion capture in games. And this was shade and shot. As you can see, when you perform jumps in a competition, it has a very different environmental context to when you perform studies in the lab. But studies in the lab are almost always the first step towards understanding a movement. Once we understand the baseline task and how it's performed, we can then progress further to see how it's done in competition and understand if I really want to get over the defender, sometimes not only to dunk, but to take a shot or to finish a layup, what must be the strategies of our whole body level coordination and post generation that we must do. So now I'll wrap it up with the overall significance and conclusions. To quickly recap my both descriptive and hypothesis-driven aims, we looked at the generation of impulses in baseball pitching by each leg, as well as characterizing whole body and segmental angular momentum in baseball pitching, particularly when it compares to ball speed. We looked at how impulse were generated during running jumps to redirect the body's momentum, and what are the biomechanical differences between jumps with and without a basketball. And we actually were able to explain some differences in jump height. Lastly, we looked at the different biomechanical factors behind jump heights from an impulse and momentum perspective. Our key findings first relate to the fundamental descriptors of movement control in the task of pitching and jumping. In pitching, we found that each leg plays a distinct role in regulating the body's momentum, and they leverage different mechanisms to do so. The roles of the back leg also evolved from forward propulsion to rotation generation. And the implications are that we provided a mechanical rationale in terms of coaching behind reading the drag line and understanding different strategies. In terms of running jumps, we found the dominant role of the first leg towards upward acceleration of the body, as well as participant differences in backward acceleration of roles of each leg. And the implications are that we provided previously lacking mechanical context of technique and joint loading in the task of running jumps. And we were also the first study to reveal that the backward acceleration task can be done in multiple ways. In terms of understanding biomechanics against performance, I found that angular momentum was transferred from the lower limb through the trunk into the throwing arm, and that whole body trunk and pitching upper arm angular momentum associated with ball speed positively. So the implications are mainly about how much more future research we need to understand the variable of angular momentum during baseball pitching, even though we were the first to characterize the profiles of whole body and segmental angular momentum. When comparing jumps with and without a ball, we were able to explain a difference in performance, aka lower jump heights, with differences in either initial momentum and upper impulse. And the implications are that we should prescribe specific practice for each of these tasks, and also expect and embrace participant differences when learning sports-specific movements. And lastly, we found that jump height correlated with whole body kinematics and kinetics variables in both jumps with and without a ball. And the implications are to develop physical qualities that allows us to use more of these variables to help improve performance and obviously keep practicing the specific task. So now, even though we've identified biomechanical variables that relate to performance, there are still things that we need to keep in mind. Firstly, even though there are variables that correlate with performance, the first question we should ask is, can they be readily modifiable? Can I give you a cue to help change how you're moving in the next rep? Well, some examples of not readily available biomechanical variables could include limited ground action force capabilities by this participant at this specific time point. This participant might not simply be strong enough or have the requisite coordination in terms of the skill to demonstrate or generate enough forces to allow you to accomplish the task. Additionally, the task constraint could also limit the ground action force generation. And really the solution for this will be to take a long-term development perspective to eventually address these limiters over time to then hopefully change this biomechanical variable over time rather than in the short run. Additionally, there might be variables that correlate with performance that's too difficult to modify directly. For example, movements can be happening too fast for you to modify what's happening at the last 10% of the movements. And this is the most pronounced in the pitching movement, where it's very difficult to change how your wrist is rotating just before you're about to release the ball because it's all happening so fast. In coaching, as I've seen from my internship with the Phillies, is they were doing a lot of indirect modifications by changing the setup or changing the initial conditions. Or you can do repetitions with that slight change in mind, and they use biomechanical tracking to see if that changes in the setup actually results in changes later on down the line. And lastly, there's almost always athlete differences, but it not only manifests in the biomechanical variables. So one biomechanical variable that can be beneficial for one can be detrimental for another. One athlete may need more velocity to jump higher, but for others, they might have too much velocity, so they need to reduce it down. Additionally, they can also have very different movement strategies and also training response to different training stimuli. So we also have to keep an individual-based perspective. So the overall recommendation for incorporating biomechanical variables to track performance and understand performance is to use variables that's most related to the task and mechanical objectives of the movement, such as the impulse and momentum variables, and then contextualize those with understanding how and why each athlete moves the way they do. So I want to acknowledge my professor for all these years of support. My now Dr. Mitchell Tillman, who's been with me since my very beginning until the final year. Zahava and Aaron especially for baking the baseball and basketball cookies. I'd like to thank my committee members, Dr. Nataraj, Dr. Zanotto, Dr. Gan, and Dr. Kip, who's joining remotely. I'd like to particularly thank my two undergrad helpers that helped with a lot of my data collections, and also Stevens funding sources, which included the Provost Doctoral Fellowship and the Doctoral Excellence Fellowship, as well as the MLB research grant that supported the baseball pitching studies. I'd like to thank my collaborators and co-authors from Rush, which include Dr. Chris Knowlton, Matthew Gauthier, Zach Traub, Nikhil Verma, Gregory Nicholson, and Anthony Romeo, who are all collaborators and co-authors that were instrumental in getting this research grant. I also like to thank Dr. Jill McNitt-Gray, who's joining from USC, for all of her questions and guidance at the very early stages of my research, especially all of the so what questions. I'd like to thank all of the coaches I talked with on Instagram and all the study participants, volunteers, and other mentioned undergraduate student helpers. So with that, I conclude my initial talk and I'll answer any questions.
And for questions? Maybe just one of the Zoom.
Yes, yeah, I'll do this.
So this is the open question section. We'll pick everyone out except the dissertation.
Yes, Sophie.
Well, this is, has this helped you with your jump height?
That was a lot of the motivation. Okay, so there's a joke in sports and training. So if you're a great athlete, you obviously go pro. If you're not that good, you become a coach. If you're even worse, you become a researcher. So a lot of us goes into sports research with the goal to help ourselves. But I jump the same height. But the way I'm jumping looked better. So I might be weaker, but I was able to have a better technique and use more of my initial conditions. So I really need to get stronger, but my jumping looks a lot better.
What about your baseball pitching?
It's too bad.
So there is additional matrix to evaluate.
There's
In
the-
addition to the height. Yeah.
But you're overcoming the leg atrophy from doing all this computer analysis, right?
I hope so. I hope so.
I mean, I'll